Today we will discuss about cooling tower calculation. Okay, before that we will just see the basics. So I have, if you go through my folder, there is a codes and standards, calculation and design guide. Okay, so inside the design guide, I have lot of documents. Okay, uh, so if you go through, say one of the document, okay, you will find cooling tower fundamental. Okay, so this is the basic to understand the cooling tower package. Okay, so here you can see the condenser water system. Basically, when you have a chilled water system, okay, you have as I told you before, there are two type of chiller. There is one is air cooled chiller, one is water cooled chiller. So where
Yes.
air cooled chiller, the condenser will be cooled by means of air, and whereas the
Mm-hmm.
water cooled chiller, the condenser will be cooled by means of condenser water. Okay, so
Yeah.
basically the
Yeah.
condenser water, you have a different component. Say condenser, this is a part of the chiller. Then you have a
Mm-hmm.
condenser water pump. Then you have a condenser water piping. Then you have a cooling
Mm-hmm.
tower. Okay.
Yeah. Yeah.
So we have seen that condenser as a part of the chiller package, right? Okay.
Mm-hmm.
Then the condenser water pump. This is like to push the water from cooling tower basin, okay, to the condenser part of the chiller. Then again it will back to the your cooling tower. Clear, right?
Okay.
Okay.
Yeah.
Then the condenser water piping. It's a piping circuit so that it can travel. The water can travel through the piping network. Okay. Then there is a cooling
Mm-hmm.
tower. So in this cooling tower, we have a different components. So if you go through another page, okay, this is the cooling tower fundamental. Okay,
Okay.
so where you will see the different type of cooling towers. Okay,
Mm-hmm.
there are
Mm-hmm.
two types basically. One is the uh, atmospheric type, and another one is
Mm-hmm.
the forced ventilation. Okay,
Okay.
so if you go to there is another sheet which is called let me open another pages.
Mm-hmm.
So this is the we have seen basically there is a chiller, you have a condenser part, so this water will be traveled to the cooling tower, then it will cool down. Then after that, it will be pumped to the condenser again through the condenser water pump. Okay, so
Yeah.
this is the schematic diagram.
Mm-hmm.
Okay, here you can see basically the design of cooling tower. Okay, a cooling tower is
Mm.
a semi-enclosed device for evaporative cooling of water by contact with air. So basically, the water is getting cooled by means of contact with air. Okay, the atmospheric air will cool the condenser water. Okay,
Yeah.
so here, as I said, there are two type of cooling towers. One is the atmospheric type. You can see the classification of air
Mm-hmm.
draft cooling tower. One is atmospheric type.
Mm-hmm.
Then another one is called mechanical draft tower. Okay, clear, right?
So what about the natural draft tower? There's atmospheric tower,
Yeah,
natural draft.
it is also similar to natural draft tower. Okay, you can if you go to the
Okay.
fundamental, you can see there are different type of cooling towers. You can see that natural
Mm.
draft cooling tower, right?
Okay. Okay.
Okay, so the air will be in through the atmospheric, then
Mm-hmm.
it's like from the atmospheric air will be entering through the tower. Okay, in this tower the
Mm-hmm.
air will be traveled on the top of the tower. Then it will be cooled down, like the water will be sprayed on the top of the cooling tower. Then it will have
Mm-hmm.
a contact. Okay, so it will be cooled. So
Mm.
if you see that atmospheric tower, okay, without any fan, atmospheric spray tower is nothing but without any fan. Okay,
Okay.
okay, so here you can see that the water inlet on the top of the tower. Then there is
Yeah.
you can say that like you can say like jet or like a sprinkler kind of thing where the water will be
Okay.
uh, divided into multiple particles. It is same like our shower in the bathtub. We have a shower, right? So you can say
Mm-hmm.
that the water will be converted into multiple particles. Then it will be fall like from the top of the tower to the bottom of the tower, like there is a basin. Okay, so
Mm.
when the air pass through the, say for example, you have a air pass through that cooling tower, right? You can say the
Yeah.
cooling tower. Okay, so that will
Yeah.
cool down the water, right?
Mm-hmm.
Okay, so this is one of the type. And you can say that there is a counter flow and there is a cross flow. Okay, so when you say counter flow, it is nothing but the water will be sprayed from top of the tower to the bottom of the tower. Okay,
Okay.
whereas the air flow will be from the bottom of the tower to the top of the tower. So it will be counter flow.
Okay.
Okay, so this is one
Okay,
of the type.
you mean to say, but by default, your pipe work is always like the jet of throw of the water will always be from the top, right?
From the
It's
top
never
only, yes. It will be from the
from the
top.
top only.
Yeah,
But
yeah,
it's
yeah.
just that in the counterflow scenario, you said the air, like you said, would always go from the bottom to the top, right?
Yeah, yeah, from the bottom to the top. Okay.
Yeah. Okay.
Whereas the cross flow will be in the cross way, like it will be like a perpendicular. Okay. So the water will be from the
From the
top
top, it will be coming
to
down.
bottom,
Yes.
and the air will be from right side to left
Left
side.
to
You
right.
can say like that. Okay. So that is the
Left to
counter.
right, correct?
Yeah, left to right or right to left, whatever it is. Okay.
It could be either way.
Yeah, either way. Okay. So this is the
But then how will the because I mean I just wanted to understand when you say count in the first example the count of flow natural draft tower, you actually are giving time for the air to go all the way up naturally. But in this cross flow scenario, I mean, will the air not go up? I mean, is that not the case when you're going cross
no,
flow
it will
because
be
it is
it
going?
will be it will be going. Okay, see for example,
Yeah.
when you see this one, so it will be like when there is a there is a water spray here, okay,
Mm-hmm.
and this air will
Mm-hmm.
be passing through the perpendicular, then it will go on the top. Okay, but the cooling
Okay.
the principle will be like perpendicular. Okay, so this is one of the
Okay.
type, clear, right? And you can
Mm-hmm.
see also here, say for example, this is the cross flow, like induced draft cross flow. Okay. Then again, you
Okay.
have a two type of mechanical draft. Okay. Now, when you come to the forced draft, like the forced draft nothing but mechanical draft. Okay. You have a
Mm-hmm.
ventilation fan. Okay. So when you have a ventilation fan on the bottom, okay, where you are forcing the air, right?
Okay.
Okay, to the towards the spray. Okay, like it is like this, you can see the picture, right? So this is the
Mm-hmm.
ventilation fan, say for example. So you are forcing the force that airflow into the cooling tower. Okay,
So you're basically just switching on the fan and then the air is generated and it's just going up directly.
going up directly. Okay, so this is the forced draft. Okay,
Okay.
and when you say induced draft, the fan will be on the on the top of the tower. So here
Oh,
the fan is bottom of the tower, and here the fan is top of the tower. So when the fan is on the bottom of the tower, it is called forced draft, and when the fan is on the top of the tower, it is called induced draft.
okay. But then, but even in these two cases, also the chilled water pipe will be coming from the top, right?
Yeah, from the
The
top,
condenser
everything,
wall.
everything. See, you can see that the water sprays, right?
Yeah.
The
Okay.
water spray here, and here also the water spray here.
Can you zoom the second image, please? I just want to see where the airflow is happening. Yeah.
See that water flow here? Can you see?
Yes. Okay.
Okay. See, this is
Mm-hmm.
basically it depends upon the type. Okay. Now, for example, when you go to the forced draft or the cross flow or the counter flow, okay, it having a various
Mm-hmm.
dimensions and various efficiency. Okay.
Okay.
So that normally you will find out when you do the proper selection for that particular location. You will find out the proper efficiency. Depends
Yeah.
upon the space. Okay, depends upon the
Yeah. Yeah.
dimension. You will select it. Okay, we will not talk about like which one is more efficiency, which one is less
More
efficient. No,
efficient.
it is not like that.
Mm-hmm.
It is depends
Okay.
upon the project to project. It will vary, and sometimes maybe you have to go with lesser efficiency, but there is a different type. Say for
Mm,
example, you have to go with the cross flow type because there is a less
mm,
space. Okay, where
mm.
you can go with the uh, counterflow where you have a more dimension, something like that.
Mm.
Okay, so that type
Understood.
it may
Understood.
vary. Okay, so this is the small types. Okay, so when you go in detail, okay, if you go, you can see one of the picture. Okay, like this is the induced draft counterflow. Okay, you can see that air is from the side,
Mm.
from the side, and it is going to the uh,
Top.
counterflow. It is like parallel to the water, like
Yeah,
the
yeah,
parallel
yeah,
flow.
parallel to the water.
Yeah,
Basically, when the
water.
water is
Yeah,
sprayed from the top, the air is
yes.
going from bottom to top, basically.
Yes, and if you see this particular type, it is a film. The film is here. Okay, the fill. You can call it as a fill. So when the air pass through the fill, it will cool down the water. Then it will go on the top of the tower. Clear, right?
Yeah, this is the where you have the fan in the top,
On
right?
the top, this both are fan in the top. So this is called induced draft.
So the okay, you mean to say within the induced draft itself, there's a
You have a two type.
counterflow and
You have a
the
two type.
okay,
Yes, I think the forced
okay.
draft also you have a two type. I guess. Okay, forced draft also. Can you
Mm-hmm.
see that counterflow? This is the counter flow.
Ah, okay. Hmm.
Okay,
Hmm.
and uh, uh, there is no picture for the cross flow. Uh,
Hmm.
Maybe the
Hmm.
cross flow may not be applicable for the forced draft because the fan is located on the
In the
side,
bottom again,
on
and
the
so
bottom and the side.
the air,
So
yeah,
you may
it's
cannot
moving.
you cannot have that cross fill.
But basically, this for in the forced draft, you like you said, in the fourth, the fan will be like a separate component. It's not like with along with the cooling tower,
No,
right?
it's
It
along with the
can
cooling
be.
tower. It's along with the cooling
It's
tower.
okay. So even if, but if we want to replace the fan, means it can be done separately without affecting the existing component in itself, right?
No, you have a duty standby, right? When you have a cooling tower, also you have a duty standby. So when one is working,
Okay.
one is another one is not working, you can have that duty standby.
Okay. So that is okay. Okay. So it doesn't really matter like that. Okay. Understood. Understood.
Yeah.
Yeah. Yeah.
So you can see that this is one of the forced draft. You can see the fan in the bottom. Okay.
That's a natural
Yeah,
draft,
this is a
right?
natural draft, but normally, yeah, this is like a natural draft. Okay. The air
Mm.
will be forced through that one. You can also see fan assisted natural draft. So there is a fan also here.
Okay. 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 Okay.
So you
Mm.
have a forced natural, and also you have a when you say fan, it is nothing but you can say that it is a forced ventilation.
Ah, okay, okay. Yeah,
So
basically, whenever you're using a fan, means you've already broken the natural consequences of it. It's all mechanical after
yeah,
that.
it's a
Yeah.
mechanical. So you can see one of the picture where you have a cooling tower, set of cooling towers, where you have a
Mm,
fan on the top. Okay, then you have a
mm, mm,
this is the condenser water pump. Okay, it will take the
mm,
water from the basin and it will go to the condenser of the chiller. Then again it will come back
mm,
to the top of the cooling tower. Okay,
mm, mm, mm,
so these
mm,
are the things you can see the pictures, the big cooling tower. Okay,
mm,
and if you
mm.
go to
But how many of these cooling towers have we actually used like in projects? Like, have you used all the cooling towers that you've shown right now? Because or
basically in our building project, we normally use the forced ventilation because when you use a
okay,
natural ventilation, you need a large size of the vessel, the cooling tower.
the
You can
cooling
say
tower in
that
itself will be
you can
big.
say the
Yes,
tower.
yes.
The tower is
Mm,
it's a very big one because it's a natural ventilation, right? You have a
mm,
lesser
mm,
flow. The flow will be very
mm,
less. So the cooling
mm,
of the
mm,
tower will be very less. Okay. So where they will use
mm.
it, say for example, if you have a large plant, okay, where you cannot consume like a large amount of electrical power. Instead of that, they will go to the large amount of spray. Like it is called like basically the industrial projects. Okay, like where you can
Okay.
say the plant rooms. Okay, maybe you can see some of the picture. Like you
Mm.
can see this picture. It's a very
Yeah, yeah, yeah.
large tower. Okay,
Mm,
where
mm.
if you have the, like this conical shape, normally you have you seen uh, uh, normally whenever you go to the between the two buildings, you will see that airflow, right? Have you seen that
Yeah.
when you go between the two building, you will have a lot of wind, right?
Yes, yes,
So
yes.
the same concept is applied here as well. Okay, when you have a larger amount of cooling tower, the air will be
Mm,
forced to to the tower inside, and it will pass
mm,
through that. Okay, so that is one of the basic concept you can just for your idea. Okay,
mm, mm,
and
mm, mm,
basically you can see that uh, there are different components. Okay, if you go, you can see, for example, there is a water in, then water out. You can say this is called,
mm.
you can say forced draft, right? You have a fan here.
Yeah.
Okay, so the air is in and it will pass through the tower, then it is out. Okay, so this is, you can say
Mm.
that forced draft. Okay,
Forced
and
draft.
yeah,
Yeah.
forced
Mm.
draft. Okay, and when you see this particular one, you can say that it is called induced draft because the fan on the top. Okay,
The fan is yeah. Wherever you have the fan on the top, it's induced, and wherever it's in the bottom, it's
it is
forced.
called forced
Right?
ventilation. Yes, so that
Forced.
basically,
Yeah.
okay.
So
Uh,
okay, okay,
yeah,
okay, okay. Mm.
but normally if you see the building projects, you will find out normally the induced draft
It's the
because the fan
induced
is,
one. Yeah.
yeah, because
In the top.
there is a lot of space required for the for the ventilation fan.
Mm.
Just to accommodate within our project, we may go with the induced draft type because the fan is on the top within the encased within the enclosed pack. Okay,
Yeah.
so
Yeah. Yeah.
as a dimension wise, maybe this is suitable. Okay,
Suitable. Yeah. Yeah.
so you can see that as a cooling tower, you can see the product, the type of components. Like you have
Yeah.
a water spray, you can say nozzle. Okay, then you have a
Mm.
fan. Then you have a heat exchanger is nothing but condenser. What condenser? Okay, then you have a pump, condenser water pump. then you have a
Mm-hmm.
basin. Okay. Okay. Now what is happening basically whenever you do the selections? Okay. We will go through some more picture. Yeah, here also you can see that fundamental like cross flow. Okay, so you can say that R is a perpendicular, right? You can say that water inlet
But
here.
that's cross flow, right? If
Yeah,
I'm
this is
not
the
wrong.
cross flow. You can see that there is a fill. Okay, this is the fill, and the water will be divided into multiple particles here in the fill.
So what is this fill basically? What are we trying
Uh,
to say when we're saying
yeah, see
fill?
when you say fill, you can see that components. Can you see here? It is like uh, you can say
It's
that
like this honeycomb structure.
yeah,
So
yeah,
water will
yeah.
basically be dropping onto it, and then the air basically. But the air and water they don't mix or anything, right? It's just like it's inside like a heat exchanger essentially,
No,
right?
it will mix basically. It will mix.
It will mix. Ah,
Yeah,
okay,
yeah,
okay.
yeah, yeah. Okay. So this
Ah,
is called
okay,
like you can say that film fill. Okay. Like it. This is like a like pad. Okay. When you say
okay.
say for example you take a towel. Okay. When you try to open the towel in a vertical direction. Okay. When you try to
Yeah.
fill the water on the top of the towel, what will happen? The water will be absorbed by the towel, right?
Yes, yes,
Okay. So
yes.
then when the air pass through the towel, what will happen? That the air get cooled, right?
Yeah, the air
That means
gets cooled and
yeah,
the
that
towel
means
gets
it will
dried
yeah,
because yeah,
yeah, it because
yeah.
it will try to absorb the heat from the towel, right? Basically.
Yes, yeah,
Okay,
yeah,
so
yeah.
that the same concept is here as well. Okay, so this is called
Okay,
film. Okay,
okay. So
and you can
basically,
say
your water basically trickles down to this fill. That's why.
yeah, yeah,
But this is why I wanted to ask. Instead of having a jet, why can't we just have like normal like open close gate valve nozzles instead of jet? That is it because we want to spread the water all
yeah.
across
Spread the
the
water.
fill and
Yes,
then
yes. See, when you spread the
okay.
water, what will happen? Your when you divide into multiple particles, it is easy to cool
Hmm.
down, right?
Ah, okay, okay. Rather than one, okay,
Yeah,
understood.
it
I
is same
understand
like
what
our
you're trying
shower.
to say.
Same
Yeah,
like our shower. Then
yeah,
you
yeah.
can say that there are different components. You can say that spray fill. Okay, splash fill. There
Mm-hmm.
are different type of fill components.
Mm-hmm.
Okay, and
Mm-hmm.
this is the film fill. So this is a different type. Then you have a structural wooden structure or steel structure. Okay, for the
Yeah.
cooling tower. Okay,
Mm-hmm.
then there is a casing. Okay, then you
Mm-hmm.
can say that wet deck water distribution basins to collect all that one. Then you have a intake lure and drift eliminator. Okay, then you have a fans, motors, drives. So these are all the
Mm-hmm.
components, right? So you can say that
Mm-hmm.
this particular guideline will give you all the basic components. Okay. Uh, then if you go further front side, you have a
Mm-hmm.
design like this is the cross flow, then this is the counter flow, right?
Mm-hmm.
This is the fill item. Okay.
Mm-hmm. So basically, the water just trickles down to this fill, and essentially the water passes through the fill, and then on the other side you have the air coming for if it's a cross, if it's just normal cross flow, it will just basically go from inside from the bottom, and then the
Yeah,
air
yeah.
travels all the way up to the top,
Yes,
basically.
yes, yes. Okay. So
Okay.
when
So
you
even in
yeah,
so even in this you would have efficiency issues, like for example when we say
different
like how we
different
have
ambient temperature will have a different output. Okay.
not like that. I mean to say, remember when we spoke about bypass factor and everything within the cooling coil, where you have not the like out of the 100% of the air that you're trying to throw to the cooling coil, some would not basically pass through the cooling coil, right?
Yeah,
That's the
yeah.
idea of
See,
bypass.
yeah,
Because yeah,
that is what it is here. Okay. So when you go to this particular selection, okay, what I said when you
yeah,
have a cold water,
yeah,
which is called hot water temperature, like the cooling water inlet, and
which
when
is
it
coming at
pass through the
42
cooling tower,
degrees.
yeah, when it pass through
Yeah,
the cooling tower, it should reach to the wet bulb temperature. Okay, but it cannot reach to the wet bulb temperature because of the efficiency, or you can say
okay,
that like
okay,
the bypass factor concept. Okay,
yeah,
but
yeah,
it will go as a cooling water outlet. Okay, as a cold water temperature. So when you say
yeah.
this range is called range, the
Mm,
between the hot water temperature and the cold water temperature is called range. Okay,
okay.
so when you see one of the data sheet, okay, this is the data sheet here. So
Mm-hmm,
from here you can see the selection modular type. This is the the model. Okay, the
mm-hmm,
tower model. Then you
mm-hmm.
can see that
Mm-hmm.
induced draft, double cross flow modular type. Then you have a circulating water.
Can I just confirm what is it? So this in this induced draft means the fan will be on the top, and when you mean double cross flow means
It will
The
be
air will
cross on
just.
both sides. Okay, see, this is the one. This is the cooling tower. The same cooling tower is here. The cooling tower is here, right? You can
Mhm.
say that the fan on the top, right? This is the fan.
Yeah, the
Okay,
fan
so
is on the
this is
top.
also I
Okay.
have attached as a part of the folder. You will see all the
Mm-hmm.
components here. Okay, this is one,
Okay.
two, three, four. All the component you can read here. Okay, so this is basically a
Okay.
fill. Okay, then this is the basin. Everything is here. So if you go to this particular
Mm-hmm.
one, one is the motor, fan assembly, fan hub, reducer housing, fan bearing, motor pulley, fan pulley, V belt, then reducer base, motor base, fan
Mm-hmm.
rod, fan cylinder. Okay, then you have a fill, hanger, top frame, side frame, then rod, basin frame, access ladder, diffusion box, HWV cover,
Mm-hmm.
spray nozzle. This is called a spray nozzle. That will water will be sprayed on the top of the tower. Hot water
Yeah.
basin. Okay, casing. Then you have access door, cold water basin, collection pit, walkway, vibration isolate. So these are all the components in the cooling tower. Basically, when you have a big
Mm-hmm.
cooling tower. Okay, so you can say that this is the outlet of the cooling tower where you have a collection from the basin. It will go to the condenser. Okay, so here you can see that
Mm-hmm.
condenser. Okay, whereas if you see on the top, you can see there is a nozzle. Can you see the nozzle here? This is a
Yeah.
nozzle. So this is the inlet, and the nozzle will divide into multiple particles, and it will go through the
Pass through the fill.
fill. Okay, fin.
Yeah.
You can say the fill. Okay, fill.
Mm.
You can say. So when the water is multiple into more particles, then it is easy to cool.
Mm-hmm.
So then
Mm.
your air will be passed through the fill. So this is called cross, right?
Yeah. Yeah. Okay. Okay.
So
Okay.
this is the same
Mm-hmm.
same selection. Okay. Uh,
Mm.
if you go to the data sheet, okay, then you have a circulating water. How to calculate circulating water? You know the formula, right?
Yeah.
The GPM condenser is nothing but TR multiplied by 30
Uh,
divided by delta T. Okay.
by
The
delta T.
delta T
Yeah.
is given here. Okay.
Okay.
And here you can see the wet bulb temperature, 28 degrees Celsius.
Yeah.
Clear?
But
Okay.
your wet bulb, no, but this is my question. So I wanted to ask you this for the evaporator also. I let me finish off the condenser first. But in this scenario, when you say delta T, it will be say if it is 46 and 29, we have to minus 46 minus 29, or
No, see, when you want to calculate range, okay, if you
mm,
go to, say, for example, if you want to calculate range, it is difference between the cooling water inlet to the cooling water outlet.
okay, that's all.
This
Okay,
is the
all right,
range.
all right.
So when you see the
Okay,
approach, okay, the approach is nothing but the cooling water outlet to the wet bulb temperature.
minus the 29.
Okay.
Okay.
So the more the approach is very lesser, that means you are able to cool more efficient, right? So the approach should be
Okay.
lesser and range should be more, basically.
Mm. Approach should be lesser and the range should be the more. But the thing is, but when we do this, this range is essentially the GPM for a condenser, essentially, correct?
No, no, it is not a GPM. It is a temperature difference.
Okay, range is okay. So range and approach are actually temperature
Yeah,
differences
it's a temperature
that we need to
difference.
be
This is also
that
temperature
do needs to be
difference.
understood. Okay, but let me ask you something here. So when we are trying to find the GPM for a condenser, when we say the
Thirty divided by delta T.
tons into 30 divided by delta T, correct?
Yeah,
So the tons is the tons that you get from your selection. Okay, 30. Then the delta T would
this delta
actually
T.
be the,
That
yeah,
is not
okay. Your
nothing but
will be your
range.
range essentially.
Range,
Okay.
range. Clear, right?
Okay. Yeah, yeah, got it.
Okay, so this is the range. So normally, whenever you see any of the project, okay, you may calculate the cooling tower. Say, for example, this is the cooling tower efficiency. Okay,
Yeah.
then you will be
Mm-hmm.
calculating the range.
Mm-hmm.
Range is nothing but hot water minus cold water temperature. Then you have
Yeah.
approach cold water temperature minus wet bulb temperature, right?
Okay. Yeah. Yeah.
Okay, so if you go through my Excel sheet, also I have given the definitions. What is the approach? The approach is the difference between the cold water temperature, leaving the cold water, and the wet bulb temperature.
That bulk temperature.
Okay, then the cooling tower approach.
Mm.
Okay, uh, is the cold water temperature minus wet bulb temperature. So this is the approach. So if you go to the picture, you can able to see very clearly. So by using this one, you can calculate range and also you can
Mm.
calculate approach, right?
Mm. Mm.
Okay. Now what else we have to calculate? We have to calculate the flow rate. The flow rate you can calculate like GPM. condenser is nothing but
Yeah,
TR
equal
multiplied by
TR, yeah,
del,
30 divided by delta T.
delta T. So you can calculate the GPM as well, right?
Yeah, yeah,
Okay.
yeah.
Okay. Now, when you go to the cooling tower efficiency, how to calculate cooling tower efficiency? This is a hot water temperature minus cold water temperature multiply by 100 divide by
Okay.
hot water temperature minus wet bulb temperature. Okay. So it is
Okay.
simply you can say that cooling tower efficiency is nothing but range divided by range plus approach. So what is the range? Hot water temperature
The
minus cold
range is
water
basically
temperature.
hot water temperature minus. Oh, okay. You mean to say like that? You mean that
Yeah.
condenser supply minus condenser return?
Yes. And when
Yeah,
you say that
and
divide by hot water temperature minus wet bulb temperature, that means
condenser
hot water
return minus
temperature
wet
to
bulb
the wet bulb
temperature.
temperature. So what is the
Hmm.
difference? This is nothing but range plus approach, right?
Yeah, 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 yeah.
So that is the way you calculate the cooling tower efficiency. Okay.
Hmm.
Then what else we have to calculate? We have to calculate the water losses. Okay, in the cooling tower.
Okay.
Okay. So when you see this picture, okay, normally if you go through one of the picture in this diagram, okay, what is happening
Hmm.
whenever you spray, whenever the water getting sprayed on the top of the
Yeah,
spray nozzle and then on the
yeah,
nozzle, the water,
yeah.
say for example, if you are supplying, say for example, 1000 GPM and you should get
Hmm.
1000 GPM, right?
Hmm.
Okay, assume that
Yes,
there are
yes,
some
yes. Yeah.
losses. Okay, assume that you are getting 1000 GPM and you are getting 950 GPM from the cooling tower, right?
Yes,
So when the
yes.
950 pass through the chiller condenser, what will happen?
There will be a reduce in flow.
Yeah,
Basically,
reducing
the
flow and
reduce
it
in flow
cannot
will
cool.
affect in the, yeah, it will not cool
Condenser,
basically.
it will affect the chiller capacity, right?
Chiller. Yeah,
Okay,
yeah, yeah.
now whatever the losses, you have to have a makeup water, right?
Okay.
Okay, so what are the losses? Basically, you have a drift losses, you have evaporation losses, and you have a blowdown losses.
Okay. What's this? Okay. The drift losses basically
Drift
through the
loss,
fan, some fans
yeah, yeah.
escaping, right?
Whenever the fan runs, what will happen? It will try to take some of the water to the outside, right?
Yes. Yeah. Yeah.
Some
Yeah.
particles. Okay, so that is called
Yes.
drift losses. So there
Yeah.
is one more also option also available. You can say that. Have you heard about drift eliminator?
Drift eliminator. No.
Yeah. See, for example, the drift eliminator you will be using in the FHU as well sometime. Okay. Say, for
Okay.
example, if FHU or AHU, whatever it is. Okay. Say, for example, this is
Mm.
your AHU, right?
Yeah.
And this is
Yeah.
your cooling coil. Okay. So when you say that
Mm-hmm.
as per standard, you should not exceed more than 500 GPM, right? 500 FPM. So that which is nothing but 2.5 meter per second. That is the standard. Okay.
Okay.
Okay, some of the time what will happen, say for example, very very big projects. Okay, example, when I was working in the Dubai Hill Small project, what happened? There are a
Mm-hmm.
lot of changes. Okay, so what happened? The
Okay.
AHU capacity got changed. Okay,
Okay.
say for example, there is one room here. Okay, there is one building. You know that there is a fit out job, right? Say for example, there is one shops, so there is another shops. Okay, what will
Yeah.
happen?
Yeah.
Sometimes they will try to combine with the two was a one shop.
Yes.
So what will happen when you do the heat load calculation? The airflow rate will be much higher. So they then
Okay.
the design is already done based on certain capacity and based
Yeah.
on certain AHU model. Okay. So when you do
Yeah.
the revised calculation, your AHU flow rate will increase, right?
Yes.
Okay. So what will happen? You cannot go with the new AHU. Just you cannot that avoid damaging this AHU and you cannot buy new AHU. Sometime if you want to save the cost. What they will
Okay.
do,
Yeah.
the velocity is increasing. Say for example, 2.6 meter per second or 2.7 meter per second. When the flow rate
Mm-hmm.
increases, based on the cross section, your velocity will increase, right?
Oh, but you mean to say this 2.5 meters per second? You mean to say it's like the airflow from the HU to the space, or
No, no. See the AHU having a rectangle box, right? So
yes?
it is like nothing but ducting, duct, right?
Okay.
So when you calculate the velocity across the AHU,
Okay. You mean to say within the HU itself,
yeah,
the air
yeah,
should not travel more than 2.5 meters per second.
2.5 meter per second. Okay. What
Okay.
will happen?
Okay.
Why the standard is fixed? If it goes more than 2.5 meter per second, it will try
Hmm.
to carry some of the water particles from the cooling coil, right?
Okay.
So that
Oh,
water particles,
you
what will
mean,
happen?
okay? Whatever condensation is happening from that, you mean to say that water? Okay. Okay. Mm,
So
mm.
this water will carry through the ducting and it will go to the spaces, right? So where you
Yeah.
will see the lot of condensation will happen around the false ceiling and it will damage the false ceiling.
Damage to fall ceiling.
So that is why what they will do, they will install drift eliminator. So
Okay,
drift
okay,
eliminator,
okay, okay.
what will happen when the air will not go directly, it will try to go like, the like it will pass through. You can say that like louver kind of thing. You can say, okay, just for
Hmm.
understanding. So what will happen? The velocity of the air will be like reduced.
Reduced.
Then
Yeah,
then it will try to drop all the water particles in the drift eliminator. Okay, then it will be collected by means of the tray. Then it can
yeah,
carry through the CDP, condensate drain pipe. Okay.
yeah, yeah, yeah.
Okay,
Okay.
so the same concept will be used here as well. You
But
can install drift eliminator to avoid the drift losses. Okay,
hmm.
but
But can
still,
I ask you
yeah,
something?
yeah.
Why is that not like a why is not like a must component in every HU? Do we add that in every
No,
HU?
no,
No.
no, no, no. If your velocity increases more than 2.5 meter per second,
Hmm. Hmm.
see you will your if you change the design, okay, your manufacturer will suggest, okay, if you use your drift eliminator, you can reduce your the water particles basically.
Yeah.
Okay.
Hmm.
Sometime
Hmm.
what they will do, the manufacturer, it's already given the manufacturing clearance, it's in production. So you want to change the design. Okay. Instead of wasting the AHU, you can add the drift eliminator as a one component inside the AHU. Okay. So
Yeah.
similarly for the cooling tower, if you install the drift eliminator, you can reduce the drift losses. But assume that there is a drift. Okay. There is a drift losses. Correct?
Hmm. Hmm.
Okay. Then there is evaporation. Evaporation means what? Some of the water will be evaporated. By means of
Yeah.
what? Your hot water will be passing through the water, right? So
Yeah.
when trying to absorb the heat, you're evaporating, right?
Okay.
Okay. So that is the evaporation losses. Okay. Then what is the meaning of blow down? Remember, whenever you have a basin, okay, whenever you put water on the basin, there is a lot of scale formation, right?
When you mean basin, it's the tray in the bottom, right?
Tray
Like
on the bottom, yeah. So when the
yeah,
water
yeah, okay.
pass through the basin, what will happen? It will have
Hmm.
a scale formation. It is like the same. For example, you have a tank, water tanks. Okay. After some
Basically, the
time,
salt. You mean when you mean
yeah,
scale, it's the same salt water
same
formation
salt,
that
salt.
happens when you. Yeah. Okay.
Okay.
Yeah.
So
Yeah.
that salt will be
Deposited in the bottom.
deposited in the bottom. So there you have to remove that particular water, right? That is called
Yeah.
blow down.
Yeah. Hmm.
Okay. So when you calculate all these three losses, it is called you can say that the losses, water losses. So whenever you calculate the makeup water, you should calculate
Hmm.
these losses and then you have to give the makeup water from the potable connection, potable
Hmm.
water connection.
Hmm.
Okay.
Hmm.
So this
But then the
water,
portable water connection temperature would be different, though, right?
no, it's okay. See, when you calculate the water, when you say 1000 GPM, this will be like 2
Uh-huh.
GPM. So it doesn't
Okay.
have
Yeah,
that.
yeah, because when you said in the example, you said 1000 GPM and 950 in
Yeah,
the like
yeah, yeah, yeah.
yeah.
50,
So the
yeah.
50 GPM will it not affect?
Will
It
not
won't
affect.
affect.
Yeah, it will not
Okay.
affect. Yeah, because you are supplying cold water, right? See, it's not a hot
Okay.
water. Compared to this one, you are supplying cold water. So that cold water can go to the condenser water,
Uh,
right?
is it? Because why I'm asking this is, I mean, generally in the UAE, I mean, at least, I don't know, when you open your shower during summers, you would have hot water only coming, right? Basically, even though even if it's you're expecting cold water, you would actually be getting warm water, right? Which is not like 46
Uh,
degree, but at least you get
yeah,
my
you can
point.
say like yeah, it will be like see, normally what is the water temperature? It's 32 degrees Celsius, right? When it goes to the
Yeah,
condenser, it's 32. So normally the makeup water, you can say that it will be from the tank, right? It will be in the basement
yes,
tank.
from the tank. So during
Yeah,
summer seasons and all, it will still be hot, right?
yeah. See, actually
Um,
speaking, when you are supplying like this potable water to the cooling tower, normally they
mm,
don't prefer to take the water from the roof tank. They will be having a, say for example, you have a basement, you have a tank, right?
okay. So we have
So
to design this tank
yeah,
also, I
something
guess.
something like that. Okay, so it's not that you are going to supply hot water. It will be like a normal water, you can say, potable, normal
Mm,
potable water. Okay, so that is one of the losses you have to calculate. So if you go to my Excel sheet, okay, here it is given. Basically, you can
mm,
calculate approach, you can calculate the range. Okay, you can
mm,
calculate
mm,
the cooling
mm,
tower efficiency, as I said. Okay,
mm,
this is the
mm,
like T1
mm,
minus T2 divided by T1 minus WT. You can calculate the
mm,
efficiency. Then after that, you can
mm.
calculate the cooling tower capacity. This is like you have a Q equal to mcp delta T, same form, same equations. Okay,
Okay.
you have water flow rate in GPM, temperature difference between hot water and cold water, density of, this is
Yeah.
the same like Q equal to mcp delta T equation.
Okay.
Okay,
Okay.
now when you calculate the makeup water, you have a blow down losses, right? So you can
Yeah.
say that evaporation losses divide by
Mm,
COC minus 1. Okay, COC is nothing but the concentration of dissolved solid in recirculate water divided by concentration of dissolved solid in makeup water.
Okay.
Okay, so when you supply, when the water, say for example, whenever you circulate the water, okay, it will having a you cannot say that the quality of the water will be same in different location, right? Say for example, if you have a industrial area where you have a polluted area, okay, so when the water sprayed, it will take the air from polluted air, right? So that means your water will be polluted.
Yes.
Okay, so you can say like that, right?
Hmm. Hmm.
Okay,
Hmm. But
or
this
the
is in the
quality of the
case of
water, or the
this
quality
is
of the
in,
water.
yeah,
Okay,
but this particular formula that we're doing, that is evaporation law minus COC minus one, it's for
that is we
the
are for blow down losses. Blow down.
blow down losses.
Okay,
Okay.
so when you say blow down
But how
losses,
do
it
we
is,
calculate the evaporation loss
yeah,
then?
that I'm coming down here. Okay,
Ah, okay,
so when
okay,
you
it's
see the
coming. Okay.
evaporation losses, it is nothing but evaporation loss is 0.00085 multiplied by 1.8 multiplied by circulation rate in meter cube per hour multiplied by temperature difference.
Okay.
Okay, so if you go to one of the sheet just for easy understanding, okay, I have yeah, you can say this one. Okay, this is called draw off or blow down losses. So which is nothing but E divided by COC minus 1. Okay, and B is nothing but blow down. E is nothing but evaporation loss, and C is cycle of concentration, varies from 3 to 7. Okay, this
Okay.
depends upon the you can say that the COC is nothing but different silica in cooling tower, hardness in cooling tower, conductivity of cooling tower will vary, right? The cycle of concentration normally varies from 3 to 7. Okay,
Okay.
so it is a ratio between parameter in cooling water to the parameter in makeup water. Say for example, your cooling water is polluted, right? And the makeup
Yeah.
water is fresh water. So what is the percentage? If your cooling tower, okay, water,
Hmm.
it's not it's a good quality water. What will happen? Your cycle of concentration will be much higher. You
Higher.
can circulate
Okay.
more number of times you can circulate.
Okay. Okay.
Okay,
Okay.
so
Okay.
that depends
Okay.
upon that, it will vary. Okay, so here you can see the formula, like COC is nothing but 3 to 7 depends upon the manufacturer, which is the water. You can say that water quality. Okay,
Hmm. Hmm.
okay,
Hmm.
depends upon the location. Then evaporation loss is nothing but 0.00085 multiplied by R multiplied by 1.8 multiplied by C. So E is nothing but evaporation loss, and R is nothing but range, and C is nothing
Okay.
but circulation cooling tower. So you can calculate the evaporation losses, right?
But this circulating cooling water is
Same. GPM condenser is nothing but TR multiplied by 30 divided by delta T.
oh, okay, okay. Oh, okay, okay, okay. It's
That is a
basically the
circulating
chill,
cooling. Circulating cooling tower means
GPM
what?
condenser essentially. C is the
Yeah.
GPM condenser. R is just the temperature
Range.
between the delta T basically. That
Yeah,
is
range. Yes.
yeah. Okay, okay,
Okay. So
okay.
here you can
Mm,
calculate the evaporation losses, and then you can calculate
okay.
the blow down losses, right?
Yeah.
Okay. Then you can say the drift losses. Drift loss normally you have a different type of cooling tower. For natural draft cooling tower, it normally varies from zero point 0.3 to 1 multiplied by C
Mm-hmm.
divided by 100. Okay.
Okay.
And for
Mm-hmm.
draft induced draft cooling tower, zero point 0.1 to zero point 0.3 multiplied by C divided by 100.
Mm.
Okay. And for cooling tower with a drift eliminator, you can say that 0.01 multiplied by C divided by 100. So this is the
Okay.
equation.
So basically, the C is still the total evaporator condenser flow, right?
Oh,
Sorry, the
yes.
total condenser flow. Yeah,
Yeah, condenser
not
flow.
evaporator
Yeah,
condenser, condenser flow.
condenser
Okay.
flow, condenser flow.
Mm,
Okay.
mm,
So here you
mm.
can calculate the windage losses, like drift losses.
Yeah,
Okay.
yeah.
So by using this
Mm,
one, you can calculate the total makeup water requirement, right? E plus D
mm,
plus
mm,
V.
mm, 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 mm.
Okay, so this is
Okay,
basically you will
okay.
calculate cooling tower efficiency, then makeup water losses, you calculate range, you calculate approach, then you calculate a capacity of the cooling tower.
Cooling water efficiency was this range plus, sorry, range divided by range plus, yeah,
Approach.
approach divided into 100, right?
Yeah.
Yeah, yeah. Okay, okay.
Okay.
Mm-hmm.
And if you go through, I just download from, uh, you can also calculate the GPM, see that BT per hour divided by 500 multiplied by range of cooling, which is R, right?
Mm.
R is what? hot water to cold water, right?
That is the, yeah, that's the basically the condenser water supply minus condenser water return
Yeah,
temperature,
yeah, yeah.
basically delta T.
Then
Yeah.
there are tools to calculate the capacity of the cooling tower itself. Okay, the cooling tower
Oh,
capacity and the chiller capacity is different. Okay, the cooling tower
so
capacity will be much higher.
yeah, yeah, cool. No, no, that we have discussed like yesterday. So
Yeah,
the
yeah, the
difference
same,
between,
same,
yeah,
same.
that is because there is a factor that we have used in the formulas in itself, a 1.25
Yeah, yeah,
percentage extra.
yeah, yeah,
That is the reasoning behind it. But I understand, yeah, that there are two
yeah,
different flows between the chiller
yeah.
and the
Yes, yes,
condenser. Sorry,
yeah.
yeah, condenser. Yeah.
See here also there is one example for counterflow cooling tower. You can calculate. There
Mm-hmm.
is example determine range, right?
Mm-hmm.
You can determine approach.
Mm-hmm.
Then you can calculate tower cooling tower ton load.
Yeah.
Okay, so here this is the formula to calculate the cooling tower load,
Mm-hmm.
right? Okay, then
Mm-hmm.
you can calculate there is a correction factor. Okay, determine corrected load. Okay, then you have a select the cooling tower. Basically, this is the manufacturer will do, but just for your
Why?
understanding
What is
purpose.
the correction factor basically?
See, enter the wet bulb temperature. You have to find out here the correction factor. Okay, you can say that there is a capacity
But do we
multi.
do it generally? I'm asking because when
No,
we
when you do
discussed,
the
we
yeah, when you
haven't.
do the cooling tower capacity, you do this all these things.
No, when we do cool, no, so for example, what I'm asking is when we do our cool, like you said, we would find the GPM condenser that is based on whatever total tons we have as per our heat loads, or yeah, heat load is, and then you multiply that by 30 divided by delta T, and your delta T is basically yeah, this is one thing I want to ask. This delta T, I mean, we right now are saying using example saying it's 42 minus 32 or
Yeah, that
we
is
are
a
trying
range,
to say,
range. That is a
yeah, the
nothing but
range,
range.
yes.
Yeah.
But then when we are initially doing this in concept design, how do we how do we make find this delta T?
No,
Do
no.
we come have it?
See, this is a standard temperature, right? See, whenever you are doing
Yeah,
the building projects, you do
yeah.
based on certain temperatures, right? You cannot assume certain temperatures. Okay, so that temperature will be based on the available product.
Oh, yeah, this is what. So you will have to have an initial conversation with
Yeah,
your
yeah, of
manufacturers,
course.
right?
Yes,
Yeah.
yes,
Okay.
yes,
Yeah,
yeah,
this is what I wanted to confirm. So, for example, if I am doing a project where I have a water cooled chiller, I have to ask him what are the delta T's that you would have in your evaporator side
yeah,
and in your condenser side, basically.
yeah, yeah,
And then you take those temperatures and then you start doing your calculations based on that. Correct?
yeah, yeah, yeah. So
Okay.
basically, they will ask you. See, they will when you are going for the cooling tower selections, they will ask you what is the condenser flow rate, right?
Mm-hmm.
Okay, and what is the living temperature and what is the uh, intake temperature
Temperature that
based
we
on
have
the chiller
considered
manufacturer.
as
Based on the
based
chiller
on this.
manufacturer.
But that is for the evaporator
No,
alone,
condenser. I'm
right?
talking about condenser.
But in the okay, yeah, yeah, okay, understood.
In
Yeah,
the
yeah,
condenser,
okay,
they will ask you what is the water flow rate and what is the
yeah,
leaving temperature, what is the inlet temperature. So based on that, they
okay.
will do the design the cooling tower capacity, right?
Okay, yeah, yeah, I think I got a bit confused. Sorry, I understood what you're trying to say. Yes,
Yeah,
yes,
yeah,
because with the, yeah, when you're speaking to a chiller manufacturer, that is what you get the temperatures from the evaporator and the condenser side, in both of them, and then based on that you work your way to find your flow rates for your evaporator and condenser separately, and then once you get that, you go back to your cooling tower manufacturer. You basically have to, you have to say what is your range, what is your approach. So range being the temperature difference between the chilled water supply, sorry, condenser water supply and condenser water return, and then the approach being the difference between your condenser water return and wet bulb temperature. So you get those, yes, and then after that, you are actually going to give these info as a start for your manufacturer to start looking into. So then you would say that they will come back to you with selections like, okay, these are the different types of cooling tower they have as
yeah.
part
The
of their
dimensions, the
manufacture.
efficiency.
Yeah,
Then
yeah,
you
as
can
per,
do the selections. Yes.
yeah, and
Okay.
then
This is the
in
basic
that we
calculation.
for
This is the basic calculation. What you are doing.
yeah, and then after that also need to calculate the makeup water. So this is also done by the cooling tower manufacturers, or this is something that we have to do separate.
We can do no. Actually, we can do with the help of cooling tower manufacturer, right? They will tell you that what is the
Ah,
drift losses, what will be the blowdown losses, actual,
yeah,
okay, and what will
yeah,
be the
yeah, yeah.
evaporation losses. You can also calculate. Basically, you can have a value, then you can verify
Mm,
with the manufacturer. Same like when we prepare the schedule, then we verify with
mm,
the
mm,
manufacturer, then we update our
mm.
schedule based on the manufacturer, right?
Yeah, yeah, yeah,
Okay.
yeah.
So now if you see
Okay.
here, okay, for example, you calculate the cooling tower. ton. Okay, how to calculate cooling
Yeah.
tower ton? GPM multiplied by 500 multiplied by range divided by 15. Right, this is the 15,000 BTU per hour per ton. Whereas if you go to chiller, you have a 12,000 BTU per hour per ton.
This is what I okay. Hmm.
Clear, right? This is the
Okay.
equation
So
for
we
the
have to okay. This also we
yeah
have to say in ton. Yeah.
yeah
Okay.
yeah yeah. If you go through this book handbook,
So even in the so you when you're trying what you're trying to say is even for cooling towers also it has a different tonnage basically.
yeah, cooling tower have a different tonnage. Yes, so that is a
Uh,
15,000 BTU per hour.
mm, Okay. Because I was thinking it's the same as what your cooling load is essentially. That's what I think I wanted to confirm. Total
Yeah,
heat
you can see that
rejection.
around 15,000 BTU per hour, right? The refrigeration system total heat of rejection. Okay, you can say that for the cooling tower it is 15,000 BTU per ton.
Mm-hmm.
Whereas for the chiller it is 12,000 BTU per hour. Okay, now you calculate the tonnage, right? This is a tonnage.
Mm-hmm.
This from the for the
Okay.
cooling calculate tower ton. But we have to calculate the actual tonnage, determine correction factor. Okay, so you can say that enter the wet bulb temperature, wet bulb correction. This is the wet bulb correction, right? Okay, so chart one. This is a chart one, and you can
Mm-hmm.
say that the range is 18 degree, which you calculated here. So this is
Mm.
the 18, right?
Mm.
And this is your wet bulb temperature line.
Okay.
Okay, say for example, your wet bulb temperature is 76 degrees Celsius Fahrenheit. So this is
Okay.
76-degree Fahrenheit. So here
Mm.
you can go down. Okay, so what is this one? This is the approach line. So approach line is how much? 9 degree. So this is a 9 degree, right?
Mm. Mm.
So when you go here, you will find out the capacity factor.
Okay.
Okay, so the capacity
Mm.
factor is 0.65.
Okay. Mm.
Okay, so when you go here, this is the
That
you
is
can say
basically the
that this is
corrected
the range
factor.
line. This is the range line. You can see the range line, right?
Yeah. The corrected factor is basically that is the corrected factor which you're leading to that
Yeah.
point
See,
between
this is
point
the
6
range
and
line.
point 7.
Okay, this is the range
Yeah.
line.
Yeah.
Okay, so
Yeah.
you can say that
Yeah.
range is nothing but 18-degree Fahrenheit. So when you cross the
Yes.
18-degree Fahrenheit, you can able to intersect
Between
this
yeah
line, and this
and
line. So you
and
will
this
get the
horizontal
correction
line.
factor, which is
Yeah.
0.65.
Hmm.
So when
Hmm.
you multiply by the cooling tower load multiply by 0.65, you can able to calculate determine corrected load.
Sure. Yeah.
Okay, then
Yeah.
select the cooling tower load by means of say for this is one of the brand. Okay, so choose the model that has a capacity equal or greater to the corrected tons calculated load.
Hmm.
So this is the way
Yeah.
you calculate the cooling tower capacity.
Hmm. Hmm. Hmm.
Okay, so this cooling tower capacity is not the same as chiller capacity. This is the cooling tower capacity.
Hmm.
Clear, right?
Can you repeat it once again? Sorry.
No, no. What I'm saying, this chiller capacity is different. Cooling tower capacity is different.
Yes. No, that I've understood. No, I've understood that. Yeah.
Yeah. So this is a range. You
The
go through the
chiller
range.
capacity is based on what is our heat load
Yeah, yeah,
essentially.
yeah, yeah, yeah.
Yeah.
This
But whereas
this
your cooling tower is basically based on your condenser flow that is going. That is
condenser
the
flow and what is outside
and your
temperature,
correct and the correct range and approach and the
atmospheric. Yeah, yeah, yeah.
corrected load factor
Yes,
comes in the
yes, yes,
correction
yes.
factor. Sorry. Yeah.
Okay. So here, this is the range. Then you will cross here. Then this is the approach line. Then you will go here. This is a range line. Then you can
Yeah.
able to calculate the correction factor, multiply by
Yeah.
with your calculated load. You will get the
Mm,
cooling tower capacity. Go to the model, approach the manufacturer. He will give you what is the
mm,
model,
mm,
particular
mm.
model.
Okay.
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 And if you
Mm.
go through one of the quick sheet, okay, you can say that quick sheet here. This also the capacity. You can find out here. Okay. This is all the
Okay.
capacity. Okay. You can say
Mm,
that in tier. Okay. Tons.
mm,
Okay.
mm,
So how
mm.
you calculate? You can calculate with the conditions. What is the wet bulb temperature? What is the range? What is the approach? What is the inlet temperature? You can correlate
Mm.
here. Say for example, I have wet bulb temperature 50. Okay. 15.
Okay.
Approach 12, 77, and 62. Okay.
Mm,
And what is the
mm.
ton you have calculated, right?
Okay, you have to check the other sheet, how you have generated, whatever
Yeah,
corrected
calculate.
ton, and
Then
then you
go
have
to
to
the model.
compare it here.
Go to the model. Which model you want to go? This is the model.
Yeah, yeah.
Clear, right?
Mm-hmm. So this correction factor will be different for different conditions, though,
Yeah,
right?
different condition. Yes, yes.
So it totally depends on how much your wet bulb is varying. So it
Yeah,
cannot you cannot always say it is going to be 0.6 one particular value every single time, correct?
yes, yes. This value will change. Yes.
Mm-hmm. But this load formula, can you just show me? So that is the load is equal to, it's basically Q is equal to MCP delta T. Yes.
Same thing,
So
MCP
in
delta T.
yeah, in that one, so the delta T is basically your 18 degree. Okay.
Yeah, this is the range.
Okay, you're basically just only doing the same, like it's the you're just basically using the condenser flow rate to find what your ton is basically. That's all, right?
Yeah, 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 yeah. Yes, yes.
Am I making sense? So that
Yeah, yeah.
means
See, this is the same equation. See, here what is that? It is mentioned. It is mentioned here. GPM
in
condenser
GPM,
is nothing but
yeah.
TR. This is like a load TR.
Mm,
Okay.
mm,
Multiply by 30. 30 is nothing but this 15 BT per hour. That is another unit, and this is another unit. Okay.
okay.
You're clear, right? I think if you divide by 15,000, divide by 500, it will come 30.
Okay. Yes. Yes.
So
Yes.
this is 30 and divide by your temperature, delta T.
Okay.
So the
So
same
that means
equations.
if it was an SI system, I want to understand if it was an SI system, will we be using 1.2? No, it won't be, right? I think
What
it
is
will.
what is 1.2?
I mean, if you remember,
1.25.
yeah, in the Q is equal to MCP delta T for sensible load, we say, right, Q is equal to MCP delta is equal to 1.2. I mean, the one
No, 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 no.
1.0.
That is for air. This is for water.
This is for water. So that means it should be 4.186, right?
No, I have to go to that equation. See, there is an equation for water. There is an equation for air. Okay.
Yeah, in the equation for water, I know what the equation for water, air is like 1.2 by something, but this is
Okay.
for
Okay.
water.
This
So
is
in
for
the case
water.
for water, it would be 4.186 into your flow rate. The CP that basically that is 1000 into 4.186 something. That's the formula basically. It's so we basically use 4.186 into your flow rate into your delta T, which is your range here, right? Yeah, delta T being, yeah, okay, it's correct. It's the range here, and then you would get your flow rates in kilowatt, if I'm not wrong. Now, I
Yeah.
just want, I know it, I'm just trying, I'm not trying to complicate it here. It's just that that is more easier for me. So I just wanted to
Yeah.
confirm if
See,
it
if
is
I
the same or
open
not.
here, can you see here? Water side
Yeah, yeah,
equation. 500
yeah,
multiplied by GPM multiplied delta T.
yeah.
This
Yeah,
for
that's
water
it.
side.
Basically, yeah, it's the same formula what they have used, basically,
Same
correct?
formula we have used. Yes.
Understood, understood. Got it. No problem. Got it.
Okay.
I just
So
got confused a bit there. I just got carried away with
yeah,
the
yeah.
units and stuff. Yeah.
Yeah. See,
Hmm.
and if you want to know more about cooling tower, here you will find a lot of things, but this will make a little bit complicated. Okay. You are
No,
calculating
no,
the
for
mass of
this, for me,
water.
till now, whatever we
Yeah.
have covered itself is a lot of
Yeah. That is
complicated stuff. I have to
that
sit through and
information is sufficient to calculate to select your cooling tower, basically.
cooling tower
Okay.
essentially.
But
Yeah,
if you
yeah,
want
yeah.
to calculate inside, like what is the what mass of the water, okay, and volume of air required, okay,
Mm-hmm.
heat gained by air, mass of air. This normally there is a equation is given here, but
Yeah.
we no need to go in depth for the when you are in a contractor or consultant. We no need to go in depth because this is all calculated
That
by
is all done by a manufacturer
manufacturer
essentially.
based on their product. Okay, so this
Mm,
may
mm, mm,
this just
mm,
for your understanding you can calculate. Say for example, mass of water, how to calculate. They same
mm,
MCP delta T formula, right?
mm,
Okay,
mm, mm,
so
mm.
then the volume of air required, there is an equation based on enthalpy and all, it will be here. You can say that enthalpy of water, specific humidity of water. When you
Yeah.
apply here, you will get the value, but we will not go in depth here because this you will not do in your when you are a consultant. You will not do this information. This will be available from manufacturer. Okay,
Mm, mm,
but
mm.
basically what is required for our calculation purpose, this one. This is the basic. So you will
Yeah.
calculate range, approach, cooling tower ton, okay, correction factor, calculate the capacity. Then if you want to calculate the GPM, you can calculate the GPM from there, from based on the condenser flow, right?
Mm-hmm,
Okay,
mm-hmm.
based on the chiller capacity, you can calculate the condenser flow rate. Okay, that flow
Flow
rate you
rate.
can apply
So
here.
from the condenser flow rate, you're trying to calculate what is your cooling tower
Yeah,
loads
yeah,
basically.
yeah, yeah, yeah. Basically, yes, yes. Okay.
No, I think I got what you're coming from. It's
Yeah, yeah.
just that I want to.
Yeah.
Can I
So
also ask you one thing? When we are using the Fahrenheit over here, well, I just wanted to ask you something. When we say 8 degree K and 8 degree C, is it the same? When we
uh,
say delta T, we see it in Kelvin, right?
yeah,
Generally
Kelvin
over
and the
here.
temperature. No, actually, when you say 8 degrees Celsius, when you say Kelvin, it
Hmm.
is a plus 273, right?
Yeah.
But when you see the temperature, difference will be the same.
No,
Degree
temperature
Celsius,
difference will be this. No, I understand. But what I'm trying to say is, when we say for chill water temperatures, when we say it is not 8 degrees C, it is 8 degree K, right?
uh, uh, yeah, see, what I'm saying, that is a delta T, right? Delta T, when you
Yeah,
say,
the delta T that you're trying to say when you
you
say
can
to
say in
somebody,
C
okay,
or you
what
can say in K. Both are same value.
both are same value, right? I just want to
Yeah,
confirm that.
yeah,
Yeah,
both are
yeah,
same
because
value.
I
When
got
you
a
see
bit
the temperature
confused. Yeah, yeah.
difference, see,
Hmm,
for
hmm,
example,
hmm, hmm.
I will tell you just for an example, okay, you can
Hmm.
say that 5 degrees Celsius, which may be 35 or 40 degree Fahrenheit, okay.
Yeah,
But when
yeah.
you say in Kelvin, you will say that 5 degree plus 273, that is the Kelvin.
Yeah, yeah, yeah,
But
yeah.
when you say that temperature difference between
Hmm.
Celsius or Kelvin, it will be same.
So basically, when you're trying to calculate delta T, it would be, say, if we have Fahrenheit here, I would just minus 85 minus 76 Fahrenheit, see what the delta T is, and then just add plus 273 to make
Yeah,
it
yeah, 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 yeah,
Kelvin, right?
yeah, 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 correct.
Okay, that's enough, right? It's
Yeah,
just okay,
yeah, yeah, yeah.
okay, okay,
Okay,
okay.
so I think hope this is clear, right?
Yeah, I mean, I still have to sit through it because believe me,
Yeah, no,
I'll
yeah.
have to sit
See, actually, I will tell you
through
that
it. Yeah.
whatever we are learning, it is just a basic
Mm,
for you to understand. Okay, but when you sit with the manufacturer for your project,
mm.
then you will get more information.
Yeah, yeah,
Yeah, that is
understood.
what I used to tell people. Whenever you want to practice something, don't practice based on my example. Okay, practice on your
Mm,
project what you are doing. Then you try to
mm.
get the value, try to match with your correct calculation. If you are a contractor, try
Calculation,
to match with your IFC schedule, whatever you
drawing
are doing
values,
it.
and yeah. Mm-hmm.
If you are a consultant, try to do the previous project, practice
Mm,
that calculation, whether you are getting or not. Then the same thing you
mm.
can apply in your new projects.
Got it. Yeah, understood, understood.
Clear, right?
Mm. This gives me a good, fair
Yeah,
idea.
yeah,
Yeah.
yeah, yeah.